All right, HL Physics 11. Okay, so one aspect that we have to get a little bit more detailed than the SL kids is to be able to really analyze the graphs of something oscillating and predict where that oscillator is going to be at any moment in time. Not only do we predict where, but we also predict the velocity, the acceleration, the total energy, and whatnot. So if you look in the higher level waves chapter at the back of the book, you'll see the first about 6 pages or so talks about some extended calculations and modeling of these graphs, okay? And I particularly like this section for HL math, all right? Because you can, modeling oscillators in an HL math or SL math IA would be pretty good, right? So it uses a sine function or a cosine function. It's usually a little bit more complicated, and you have all the tools to be able to do that. So I'd get you guys to figure out how to do this really well so that you might be able to hit 2 birds with 1 stone. Okay, so we already know this relationship. If I take a look at the video on the left, I have 2 springs. They look kind of different, but using this equation, I'd be able to say that the spring actually is the same. The only difference is how well one conserves energy. Okay, so if I watch the oscillations, you'll see that between both springs, okay, the period is exactly the same. And the mass, let's say that the mass is exactly the same as well. In that case, the K constant of the spring is exactly the same using the period relationship, okay? So the K constant of both these springs are exactly the same. The only difference is one, on the left, this spring is like an ideal spring where none of the energy is going to be lost. It's just continually cycling back and forth, okay? Whereas on the right, this is more realistic of springs in nature. Every time you squish and stretch a spring, the molecules bump each other, and so some heat is going to be lost, and we call that dampening, okay? So the spring dampens. Some springs, depending on the material that they're made, will dampen quicker than others, okay? And so you can see the amplitude of that spring just keeps on going down over time, okay? But both of these are the same spring, and this graph that you're seeing over here is a typical graph that you're going to see in the higher level waves chapter, which is a graph of position over time for the oscillation of a spring, okay? The distance between here and here is my amplitude. The distance between here and here, or not the distance, but the time difference between here and here is my period, okay? And with all that information, I can predict the displacement, the velocity, the acceleration at any point along its cycle. And that's what we're after today, all right? So let's start with first, analyzing the relationship between position and time, okay? So here's a typical position time graph, the same as what we have over here, just a different displacement. So we can see that my amplitude of oscillation is 10 centimeters, okay? And then the period, how could I look at that? Okay, the period is 2 seconds. Okay, now with all that information, I'd be able to predict where at any point in time that oscillator is going to be. And that's really important. Okay, that's important for people who are analyzing vibrational motion, or maybe like a thief who's trying to get past some swinging object, okay? You can be able to calculate when you have to jump, all right? But for example, analyzing where an oscillator is going to be in time, there's many actual practical applications of that. Okay, so this equation on the bottom is what you're given in your data booklet, and the only difference in your data booklet is sometimes there could be a sine here or a cosine here. Okay, the graph that we see up here looks like a cosine graph, not a sine graph. A sine graph would start here, okay? All right, so we apply a cosine function when the motion starts from the amplitude. Okay, if the motion started from equilibrium, okay, if the motion started from equilibrium, then that would be a sine function here. It's exactly the same relationship, but we just substitute cos with sine. Okay, but for this graph, since we're starting at the amplitude, it starts at cosine. Okay, so what do all these variables mean? Okay, x is my displacement at that moment in time. All right, x0 is my amplitude. Okay, and in some, if you're reading a different book or you're watching Khan Academy, okay, they might call that A for amplitude, all right? Now, cosine depends on the shape of the graph. Where did I start? Okay, omega is my angular velocity or angular frequency. Let's call it my angular frequency. Okay, why? Because 2 pi f is omega, or 2 pi over my period is omega. All right, and then t is time. So what do I get when I multiply omega by time? If I multiply 2 pi over the period times time, that's going to give me radians, my angular displacement. Okay, so how many radians have I gone? So for example, in this case, omega is going to be equal to 2 pi divided by 2 seconds, which is equal to pi per second, pi radians per second. And if I traveled 1 second, okay, if I traveled 1 second, where would I be on this graph? Well, if I read the graph, I am right here, okay? And that means that I'm at my negative amplitude of oscillation, okay? So if I was the spring, and I would be down here at the negative amplitude, okay? And that means that if I take 2 pi, or I take pi per second, that's my angular frequency, and I multiply by 1 second, I have gone pi radians in my cycle. Okay, and pi, the cos of pi is going to be -1. Okay, so that explains how this relationship, cos of pi radians is -1 times my displacement is equal to -10 centimeters. Okay, so that explains how this equation models that graph. Okay, this part in brackets, that's really important. A lot of students forget to put brackets, because when you multiply angular frequency times time, that tells me my phase. Where am I in my cycle? How many radians have I moved? And then you multiply that by cos. That'll give me an ability to multiply by my amplitude to tell me where I will be on that graph. Okay, so this equation maps that graph. Okay, so that's pretty easy to calculate. Displacement is pretty easy. It's either cos or sine, but using that function, and this is all in your data booklet. Okay, then if I go and try to analyze velocity and acceleration, this is a really good math problem for calculus. Okay, so if you want to do a calculus IA, simple harmonic motion is really useful for you. Okay, this top graph is another example of a position time graph, and it's a cosine function. Okay, the period is about 1.4 seconds. All right, now how do I convert that position time graph into a velocity time graph? Okay, well, if you remember from the kinematics unit, to convert the position time graph, you have to look at the instantaneous slope. Okay, so the slope here, let's change the color. The slope here is going to be 0. Okay, what about here? The slope there is going to be negative, and it's the maximum slope I can get. The slope here is 0. The slope here is positive, and the slope here is 0. Okay, so then if I was to convert this graph into velocity, this cosine graph would start at 0, because the slope there is 0. And then at that point, it's going to be its maximum negative slope, whatever I calculated. And then at that point, it's going to be 0. And then at that point, it's going to be my maximum positive. And then at that point, it's going to be 0 again. So you see that you can transform a position time graph into a velocity time graph by taking the derivative of that graph. For those of you taking calculus, you'll start to understand that term. The derivative of a position time graph is a velocity time graph. Okay? And likewise, if I take the slope of a velocity time graph, or the derivative of that, I will get the acceleration. Change in velocity over time is my acceleration. So what is the slope here? The slope here is a maximum negative slope. That's why it appears down here. The slope here is 0. That's why it appears as 0 over here. The slope here is a maximum positive. The slope there is 0. And the slope there is maximum negative. Okay? So all of these are derivatives. Okay? So it must be that the equation for the position time graph, the derivative of that equation would be the velocity time graph. And the derivative of that equation would be the acceleration time graph. This is important for you guys who are doing calculus, because it'd be really nice background information for an IA. Okay, and you're using your knowledge of physics to be able to do that. So let's take a look at these equations that I copied here for you guys. Okay, so this equation we know describes the position time graph, where A is, like, for example, what I wrote out before. A is x0, which is my amplitude. Okay, or in some books they say A is the amplitude. So x, my position at any time, is going to be my amplitude times cos times my angular frequency times time. Now in this case, my angular frequency is going to be 2 pi 2 pi divided by about 1.4 seconds is equal to omega, okay? So you'd have to do that first. And like I said in the SL lectures, my angular frequency of anything that's oscillating with simple harmonic motion, my angular frequency is like the fingerprint, okay? That's the blueprint of simple harmonic motion. It's the most important thing for us to calculate first, because then knowing that, I'll be able to calculate anything else. You can see it shows up in all these equations, okay? Then, after doing that, I can calculate the velocity using this next equation. So if you take a look, the only difference here is I went from cos to sine. There's a negative here, and I have angular frequency showing up in two different places. So why here? Let's talk about that first. Okay, why would there be angular frequency over here? Okay, so remember that angular, let's change the color of the pen. So angular frequency times r is going to be equal to meters per second. Okay, if you remember from the last. So 2 pi over t, that means radians per second, times r, so 2 pi r is like circumference, 2 pi r over t is going to be equal to meters per second. Okay, and r in this case is my amplitude, okay, or the x position, where am I at that moment in time. Okay, so I'm just going to erase all this down here. That explains why we multiply our amplitude times omega. And the amplitude times omega would be my maximum velocity. So that's my starting maximum velocity. So in a way, I can create another equation. If they gave me that, I can say that my velocity is equal to negative my maximum velocity. Okay, if they gave me that, times sine omega t. Okay, that's another way of saying that. Okay, so that's what AW means, or A omega means, my maximum velocity. All right. Okay, there's also another relationship which we're going to talk about in another video. Okay, using kinetic energy, I'll be able to calculate that. Okay, here's another relationship where the velocity at any point in time is going to be equal to my angular frequency times the square root of the amplitude squared minus the position at that moment in time squared. This is a very simple way of calculating. You don't have to use sine or anything else like that. So a lot of students like to use this relationship in an exam rather than try to figure that one out because they're not comfortable with this. Okay, so we'll figure that out when we talk about kinetic energy. All right, and then acceleration is just the derivative of that. Now first, before we do that, I want to talk about sine. Okay, so the derivative of a cosine graph must be a sine graph, as we're seeing, except it's a negative sine graph. So derivative of cos is equal to negative sine, okay? And that's what we saw here. So this is just a flipped over sine graph. And then the derivative of that is going to be a cosine graph, okay? So that's why we have the cosine over here. And then why omega squared? Because acceleration, as we learned in the other one, the acceleration of anything undergoing simple harmonic motion is equal to omega squared times x. Okay, so omega squared times my amplitude, if x is my amplitude, omega squared times my amplitude is my maximum acceleration. So my maximum acceleration times cos omega t, okay, is going to be the relationship. So if I just erase that, so my acceleration is going to be equal to my max acceleration, okay, negative max acceleration times cos omega t in that case. Now what would happen if I started with a sine graph rather than a cosine graph? Well, then this is sine, okay, and then that's going to be cos, and then that's going to be sine again, okay? So you just invert all those things. All right, so that's the explanation of the equations that you guys have in your data booklet. I haven't gone through any problems yet. In the next little video that I'll make, I'll actually give you guys some example problems and we can try to solve it, analyzing graphs or predicting what the graph would look like for something undergoing simple harmonic motion. It looks daunting when you look at the data table and you see all these functions, you see all these equations. It looks really, really daunting, but actually after about 10 minutes of practice, you realize that some of these questions are probably the easiest you're going to get on an IB exam. And if you practice analyzing the graphs, you're really hoping that you're going to get that. And more importantly, for you who are doing higher level physics, you armed yourself with something that you can write about when you're predicting or modeling something for a math IA. It's a pretty good relationship to explore. Or for your physics IA, it's also a very great relationship to explore. Often kids who do simple harmonic motion for physics IAs have a pretty straightforward time doing it. They know what they're trying to measure and detect, and some of you can even do this from home for your IA right now. Okay, that's it. That's all we got for this one.